Hi, everyone. Thanks for joining today. My name is Rob Rappold. I'm the VP of Business Development for Allonnia's SAFF business, and welcome to our Allonnia Insights webinar series. Today, Dr. Jason Natko will be talking about our PFAS treatment cost comparison and including what it does, inputs, assumptions, and so forth. And we're going to go through a live demo for a few different scenarios. So before we jump in, a few tips while joining the webinar today. This webinar is in listen only mode, so everyone except the presenters are muted. If you have a question, please submit the question box available on the right hand, or please submit it in the question box available on the right hand navigation of your screen. We'll have time for Q&A at the end of the presentation. And if at any time you lose audio or the screen freezes, please try refreshing the screen. So now to introduce Jason. Jason holds a PhD in civil and environmental engineering and is a registered professional engineer. He has more than 15 years of environmental consulting and research experience, primarily in the investigation and remediation of PFAS and bioremediation of chlorinated solvents. At Allonnia, Jason manages the engineering team that deploys innovative technologies at customer sites to include the SAFF, which we'll talk more about today. And with that, I'll turn it over to Jason.
All right. Thank you, Rob. Thank you, everyone, for joining this webinar today. As Rob said, today we're just talking about the treatment cost tool that we've developed to do cost comparisons between ion exchange resin, granular activated carbon, and SAFF, which is Allonnia's foam fractionation system. If you're not familiar with SAFF, we have some previously recorded webinars and some videos that will explain the technology. But we're not going to go over foam fractionation today in any way or what the SAFF does. We're just going to jump right into our cost analysis tool and go through some scenarios. So the idea of this tool is to provide a cost comparison between different technologies. As we'll go through, there are some assumptions underlying the system and it will perform some calculations, but these are not intended to be used for budgeting. They're really conceptual level costs. It will do some vessel sizing and come up with volumes and figure out how much media you may need. But these are just based on a list of assumptions and you cannot rely on these for any kind of final design. These are my engineering caveats up front. And just keep in mind, this is a work in progress. So if you are interested in the tool and want to schedule a time to go through a site with the tool, just know that things may be changing over time because as new data comes in, we're always reevaluating this tool and updating it. So to get started, the first thing you'll see is we have some places to enter different information. So we'll go through some of the inputs and how those assumptions come into the ultimate cost calculator. So the first two are pretty easy. We have inflation rates and discount rates. So whenever we look at our cost comparison, we're looking at it over time and we're normalizing all our future costs to present value. So that's done with the inflation rate and the discount rate. We've also added a tool that's not shown here, but we can add a different inflation rate for ion exchange resin or carbon, because you may believe that even if inflation is only going to be 2.7% over the next 30 years, carbon or resin costs could go much higher if there's a large demand for those. So you can inflate those differently. Then you can add site-specific costs like labor rates and electric rates, because those are pretty large drivers for your foam fractionation costs. For the next set, we get into some of our project design parameters. So flow rate is going to be a very important one. That's going to determine how many PFAS are coming in, how large your treatment units need to be. So that'll be used to size your carbon or ion exchange resin vessels based on an empty bed contact time and determine how many foam fractionation units you need. Then we can select a source water type. So we have a few different options in there, which we'll go through in the demo. But those source water types really determine your maintenance requirements for your foam fractionation system. A cleaner water like groundwater will have lower maintenance than a dirtier water like landfill leachate. And it also determines the amount of PFAS that you can load onto a resin. So if you pick a dirtier matrix, it's going to assume more competition for sorption sites and faster breakthrough for a dirtier water compared to a clean water like groundwater. The last thing we have here are some discharge criteria. So you can pick a certain discharge criteria, and then the system will determine if the SAFF treatment technology can meet that discharge criteria, or if you need some kind of polish, some kind of secondary treatment to remove PFAS. And if you do need that, those costs will be added into the calculator. So you can also input site-specific PFAS concentrations. You can either do individual PFAS that are regulated or a total PFAS value. Depending on the settings that you put in, it will give you an estimated removal percentage. Those are just based on averages that we've seen across a lot of different water types. If you did do some kind of bench test or have other performance data, we could update the calculator with those data to provide a better estimate. So then the calculator will compare the regulatory limit to your estimated effluent and determine if it needs a carbon polish or not. Then we have some specific inputs for our different technologies. So the green cells are what you would typically input, and then the purple cells are things that are looked up based on some assumptions in the software. And then that orange field is something that you can toggle on and off. So by default, it will toggle on if you need it to meet your discharge criteria. So you can see here for the SAFF, foamate disposal cost, and if you're using a foaming additive are things you would input. And then the concentration factor, again, is determined based on an average of different waters that we've seen. So that'll vary depending on what water and booster you select. If you have done a pilot test or bench testing, you can override that and put in a site-specific volumetric concentration. Same thing would happen for the carbon polish costs. There's a default value in there, but if you had already done some cost estimating, you could put in your own cost. And then we have carbon and ion exchange resin. So you'll have costs for the media themselves, the cost for having someone come and change that media, and then the capital cost for those systems. So I have built in some calculations where it will size the system based on the flow rate, and it'll select vessels and carbon volumes and give you an estimated capital cost. But I'm not an expert in designing GAC. So if you have your own capital cost, if you've already gone through that design process, you can put those in and get a more accurate cost comparison. After we put in all our inputs, we'll jump in and see what the system outputs look like. So on the left-hand side, you can see some of the outputs it will give you as far as vessel sizing. So it'll tell you how many foam fractionation systems you need, how many SAFs. If there is a carbon polish after the SAFF, how many pounds of carbon will be in that polish and how many changeouts per year will you need to do. And then it will give you what it estimates is the carbon vessel size. Again, that's based on flow rate and empty bed contact time. How many of those vessels you will need, how many lead vessels, so it assumes a lead lag configuration, and then how frequently you'll be changing out that lead vessel per year, and then the same thing for ion exchange resin. Then based on those parameters, you'll see on the right, you have specific cost breakdown. So you have your annual O&M costs, how much media you're going to use each year, the cost of that media, how much PFAS concentrate you'll produce from foam fractionation, the cost of that disposal, and then the cost of any foaming additives or boosters. And then all those costs plus those inflation rates that we put in the beginning will give you your 30-year cost for each of those options. So that's a great way to compare the different technologies. And then it'll produce these graphs that show you over time the cost for the different technologies. So with that, I'll turn it to Rob for a poll question.
Sure. Those of you that have been on our webinar series know we like a good poll question. So we're gonna continue with that today with a question kind of geared towards understanding cost profiles. So with that, I'm going to kick that off. Okay. So the question is, what is your primary water type, with the options being groundwater, industrial process water, leachate, or other? Other would include things like RO concentrate. It could be AFFF rinsate, I guess, potentially. unless you're categorizing that as industrial process water. So, but maybe that would fit under the other. So, as we're running through here, we're seeing lots of groundwater. We're seeing 58% on groundwater, 8% on industrial process water, leachate at 33%. So interesting stuff coming through. We'll give it another 30 seconds or so. We've got about 66% of the precincts in voting here. So we'll give it just, we're hit 70 now. We'll try to at least get 75 if we can. So 72% are in, 73.
All right, 77, you can call it.
There we go. We can call it. Thank you. This is really good voter participation here. So in this interesting, but maybe not surprising, roughly 60% are groundwater, with 12% industrial process water and leachate. So I'm gonna end the poll and share those results with everybody. So again, to conclude, 79% voted. It ends up 58% groundwater, 12% on the industrial process water, and 28% leachate, with 2% other. So if you put other in there, I'd be interested to know what what makes that up. Okay, with that, I'll close the poll and thank you again for participating. Yeah.
All right.
Yes.
So now it's time to move to our live demo.
Right. We're going to run into a live demo. And so maybe I'll just kick us off here. So, SAFF has shown some really great results on treating contaminated groundwater. In many of our applications, a booster is used to enhance the foaming potential of the water source. For this example, let's look at a concentration in the high ppb range based on real results from a Department of Defense site. We will also compare the addition of boosters to aid in foaming. Due to the high concentrations, we'll also add in a GAC polish step. Jason mentioned the tool's ability to do that. So we'll add that in here, which may or not be needed in an actual scenario. But for the purposes of showing the capabilities of the tools, we'll do that. So our goal is to meet the EPA MCLs in this scenario, and we assumed 100 gallons per minute for the system size. So Jason, if you want to walk us through.
Thanks, Rob. So
Sure.
Yes, this is already set up because we knew this was the first scenario. So we already have it set up. So 100 gallons per minute of groundwater targeting EPA MCLs. If we come down here to the concentrations, you can see the influent concentrations here. These are from an actual groundwater site. So they're on the higher side of contaminated groundwater. There's a military base that has contamination from AFFF. So we have some pretty high concentrations. So you can see here the estimated removal percentage, and then it shows estimated effluent concentrations. And because those are orange, it shows that we do need that GAC polish here. So you do have a GAC polish. Looking to the right on the costs, you can see here we have granular activated carbon in orange, ion exchange resin in green, and then the SAFF costs in this blue line. So SAFF has the highest capital costs, but you can see because of those lower O&M costs, you have a flatter line and you have a pretty rapid payback. So if we go over to the cost comparison tab, we can see what is driving that difference. So we do have a carbon polish. So we have 5,000 pounds of carbon on the SAFF, and we're changing that 7 times per year. Whereas if we went to only carbon, we would have larger vessels, and we would be changing those 12 times per year. So if you look at the outputs, you can see that media usage is 35,000 pounds for the SAFF plus carbon versus about 130,000 pounds of carbon each year just for GAC. And resin is in between there at 87,000 pounds. And you can see that media cost is really what drives this difference. So we have 65,000 in media cost for SAFF versus 600,000 for granular activated carbon. And then when you look at the total cost that includes those, you can see SAFF is about half the price of the granular activated carbon for annual O&M. And that's how you're able to get that payback of about 2 years of SAFF versus carbon and little under a year for SAFF versus ion exchange resin. So one of the ways to improve the economics of SAFF and improve removal is to use what we call a booster or some kind of foaming additive. So if we switch the cost calculator to use our non-ionic foaming additive, you see that line flattened out a little bit on SAFF. It got a little bit flatter. We still need the carbon polish. So if you scroll down here, you'll see we increase the removal rates by using that booster, but we didn't increase them enough. So we still need that carbon polish. But the reason for that flatter line is that we've reduced the amount of carbon that you would use in your polish by removing more PFAS from foam fractionation. So in this case, we dropped it from about 35,000 pounds of carbon down to about 20,000 pounds of carbon. So that will decrease that payback of SAFF versus GAC to just under 2 years. Now, our best case scenarios here are if we use a cationic surfactant. Now, you can't use that in all water types or in all situations, but the cationic surfactant will give you the best PFAS removal rate. So if we switch to the cationic surfactant, we see that line drop down and get a little bit flatter even more. And the reason for that is we no longer need that carbon polish after SAFF. So when we scroll down here, our removal rates are now high enough where we're meeting that discharge limit with foam fractionation alone. And in doing so, we reduce the capital cost because we don't need that carbon polish. And we reduce the O&M costs because there's no more carbon that's needed for the SAFF scenario. So in this case, we have a payback of about a year versus the granular activated carbon system. And you can see our cost went from about $400,000 per year down to about $260,000 per year.
Jason, maybe just one comment. In the second scenario where you use the non-ionic, you can see where that line flattened. So maybe just a talking point there is that the cost of the booster is still, the increased cost of the booster is lower than the cost of the additional polish. So you'll see that the booster is a way to improve removal, enhance foaming at a lower cost, relatively speaking. So we'll touch on that more in the other scenarios, but just a talking point for now.
Yeah, and that's a good point, Rob. We do have the booster cost called out here in the O&M costs. So that non-ionic booster comes out to under $10,000 per year for a typical dose.
Good deal. So that's our concentrated groundwater scenario. Let's shift gears, and we're going to make this change here in real time. We're going to focus on a landfill leachate here. So what happens if we have a dirty matrix like a landfill leachate? Despite the complex nature of landfill leachate, SAFF is very effective at removing and concentrating PFAS with little to no pretreatment. So our SAFF technology has been deployed to quite a few locations, both permanent and pilot, on landfill leachate applications. So let's look at a common scenario that factors in the typical flow rate of a landfill with some assumptions on PFAS makeup and the impact of other co-contaminants. So in this particular scenario, we will be treating at 60 gallons per minute and meeting the UCA local limit, which was a requirement for a Michigan landfill where we deployed a SAFF.
All right. So you can see I made some of those changes as Rob was speaking. So we dropped the flow rate down. We switched it to landfill leachate. We changed our discharge criteria. And then the last step here is to change the influent concentrations. So these are some influent concentrations from a landfill site that we worked on. So we have some higher influent concentrations. You can see it shifted from being mostly PFOS in the groundwater scenario to now being PFHXA. And then you can see these UCA limits are very high relative to the EPA MCLs. And that's not uncommon because you're not going to try to treat a landfill leachate down to drinking water standards because no one's going to be drinking it. So you can get these higher limits if you're discharging to a POTW. And you can see because of those higher limits, we don't need a carbon polish, even though we have residual PFAS in the effluent. All our concentrations are below the regulated limits. So what happens when we come up here is we can see why media-based solutions like carbon and ion exchange resin are not very effective for landfill leachate. So the media costs alone in the first year are in the pushing you up in the $10 to $20 million range. And you can see over time, those are just completely unrealistic costs. And the reason for that are all the co-contaminants that are in landfill leachate that will reduce the amount of PFAS that can sorb to your media. So the calculator in its default form just has an assumed sorption capacity for media that varies based on what you select. So groundwater has a higher capacity, landfill leachate has a lower capacity. We do have some options here where you could set organic carbon concentrations or total dissolved solids concentrations to try to calibrate your breakthrough to what you would actually see in practice. But when you go to cost comparisons here, you can see to try to do this with the way the calculator works, to do this with just activated carbon, you would need 50,000 pounds of carbon. So 10 5,000-pound vessels, and you'd be changing them once a month. Same thing with the ion exchange resin. You have a lot of resin, and you're changing it 12 times per year. And that's why you get these exorbitantly high costs, which we understand are not very realistic. But it does show why SAFF is a preferred option, or foam fractionation is a preferred option for landfills, because these media costs are just so high that it's not practical to treat with ion exchange resin or GAC. And now landfill leachates don't typically use a foaming additive. The landfill leachate foams a lot on its own. So we're not going to take a look at any booster performance for landfill leachate, but we can just move on to our next water type.
Jason, before we do that, just a few questions have come in. Are the GAC costs based on virgin or reactivated carbon?
It doesn't matter. You can put in whatever cost you have. So if you have a cost for carbon that you know you're paying, you can just put that in as a dollar amount. So whether it's virgin carbon or new carbon, you could put in your price. You can see here we're using about $4.7 per pound, or $4.70 per pound. So that would be the typical cost for like a reactivated carbon that's being disposed of for more reactivation. So that kind of under $5 per pound cost would be reactivated carbon.
Okay. All right.
And it's in the mid-range. A lot of these numbers come from data we received from the Department of Defense for different projects, and this is the midpoint value of different carbon costs that we saw for DoD systems. But you can adjust that. And if you've done any kind of sorption isotherm testing or column testing and you know what your anticipated breakthrough time would be, we can adjust all those on the back end of the calculator to get something more specific or accurate for your site.
Okay, Jason, another one here. What O&M costs is included for these technologies? Does SAFF cause scaling with the addition of air, which may increase O&M for SAFF?
Yep. So the O&M costs here include, for SAFF, it includes cleaning. So when you go, that's actually a good point to test this. So you can see the costs are about $417,000 a year for landfill leachate. And that has to do with the cleaning frequency that's assumed. If we switch that to groundwater and don't change anything else, oh, it added the carbon polish, that's why. All right, so that didn't work. But if we, actually I can manually do it. If we say no carbon polish, now you'll see the SAFF O&M costs are much lower because groundwater requires less cleaning. So it does factor in how dirty your matrix is and how often you need to clean the system. So your SAFF costs include cleaning the system, weekly inspections and maintenance, the media usage, electric usage, and any foaming additives. Whereas your carbon resin costs include like a weekly inspection and disposal of the media. And if there's electric costs for those, they're very low, so they're almost insignificant.
Good deal. So another question came in. Will we share the calculator? You know, we'd really like to be doing is having, you know, discussions about your particular need. And there is some nuance with using the tool, things that just, you know, assumptions that are made, but also the inputs, being accurate and so forth. So we'd really, and we'll give some contact information, but really we'd like to be able to use this to assist you in your PFAS treatment needs. And again, we'll provide some more detail on that as we move along.
Yeah, so the short answer is no, we won't share it in its current form, but it's something that we can walk through with you. So if you schedule a time, we'll walk through it for your water and go through the details one-on-one.
Yeah, that's right. Okay. All right. So for our next, so we've gone through, we've done leachate, we've done high concentration groundwater. So for this application, we're going to look at an industrial process water. So SAFF is shown to be highly effective at removing and concentrating PFAS in semiconductor and PFAS manufacturing spaces. Flow rates can vary significantly depending on the application. So let's look at something again in the 100 GPM range with a spread of high and lower chain PFAS. In this scenario, we will factor in the use of a booster to add in the removal of short chain PFAS. So again, in this scenario, we'll be looking at the MCL for the state of Massachusetts, which is the permitted discharge criteria for our Allonnia lab in Boston, and we'll treat it 100 gallons per minute.
All right. So as Rob said, we have 100 gallons per minute. We're looking at industrial process water. We're using the Massachusetts MCLs in this case. So when you come down here, you'll see there are 20 parts per trillion for the Massachusetts MCLs. And then this is the water that we saw in an industrial water source. It's a pretty interesting water because it's only carboxylic acids. So there's none of the sulfonic acids are present in this water. It's all carboxylic acids. And when we come up here to the top, we can see we do need our carbon polish because those are some pretty low discharge limits. And our lines are kind of all overlapping. So in this case, I wouldn't necessarily say foam fractionation is going to save you a lot of money because it really depends. The lines are all about the same slope. So it depends on where you start. I don't know what assumptions are causing the ion exchange and resin costs to start out a little bit higher, but you can see they're really all overlapping. But this was for a scenario where we're not using a booster and we have that carbon polish. So this site is using a booster and they're able to use the cationic booster. And you can see when we do that, it eliminates the need for the carbon polish and our foam fractionation costs go way down. So the reason the lines were all overlapping up top is because we were using so much carbon in our carbon polish that really the foam fractionation wasn't any different than just using the activated carbon on its own. Now that we've reduced that reliance on carbon and by adding the foaming additive, we now have SAFF costs that are much lower because we don't need the carbon polish and our O&M costs have gone way down. And primarily, the driver for that is actually this PFHPA, which is very rarely going to be your driver for treatment. But in this case, because it's part of the Massachusetts regulatory limit, and it's at a pretty high starting concentration relative to the other PFAS, it's really the PFHPA removal rate that determines your cost, because that determines how much is going to need to be loaded onto the resin or the carbon. So if we go back to the no booster scenario and we look at PFHPA, you see PFHPA with no booster, the removal is down at 65%. So we're not really getting a great job removing it without a booster. And that 1,000 nanograms per liter is really driving your need for additional treatment. Whereas using the cationic surfactant, we can increase our removal rates and eliminate the need for that carbon polish. So when we look at that, what it means in terms of dollars per year, to treat this water without foam fractionation is about $1 million per year just in resin or carbon. So by saving about $1 million per year, you can see over the 30-year life of this project, you would save somewhere between $20 and $30 million by using foam fractionation to reduce your reliance on sorptive media. Okay. Our last water
Jason,
tip, Rob?
yeah, absolutely. So, and there's a few questions that have come through as well. Talked a little bit about the short chain PFAS and boosters. Um, there's a question about, can the tool extend to foam frac concentrate destruction costs rather than disposal? The answer is yes. We can look at the cost of handling things. So there's right there if um, depending on what your means of destruction, disposal, et cetera, are, you can adjust the price per gallon right there, and it'll impact the cost calculator. Can you
Yeah, so
use the,
like Rob said, it's just a toggle. It doesn't care. It doesn't know if you're disposing or destroying. It just is a cost per gallon. So you can increase or decrease that cost per gallon depending on what you're doing. I mean, we've seen costs for deep well injection as low as $3 a gallon, and costs for novel technologies that haven't scaled yet, and more than $20 to $30 a gallon. So it really depends on what you do with your foam, but you can adjust that as a dollar per gallon value.
yeah. One other one that came in, can you use pilot scale field test to confirm go, no go on the booster need? The answer is absolutely yes. A few things. You could run a bench scale test and get a pretty good idea. We do those in our Allonnia lab. We use, no booster and then different boosters to compare. But also with our pilot unit that we take to sites, we do the same thing, full capability to add boosters and see at the operating site what the impact of the booster is, or if it's needed at all. Okay, so in our last scenario here, we're going to look at an RO reject. So we'll see how SAFF treats reverse osmosis concentrate. ROs can be used upstream of a SAFF in higher volume applications. MGD type sites for drinking water can be obviously huge flow rates, and the SAFF can treat the concentrate. Examples would include drinking water applications, other high flow industrial and groundwater opportunities. The salinity that comes from the concentration of the salts in the applications actually serves as a benefit to SAFF and is shown to improve performance of foam fractionation in general. For this scenario, let's look at a lower concentration PFAS feed source that uses RO to treat the permeate. The concentrate will then move to the SAFF for removal and concentration. In this last scenario, we'll look again at 100 gallons per minute and meeting the US EPA MCLs. A booster will be added in this instance to enhance the foaming. So Jason, it's all yours.
All right. So here, as Rob said, we sticking with 100 gallons per minute flow rate. We switch to an RO reject water. We're going to use the EPA MCLs in this case because likely if you're doing RO water, it's related to drinking water. And we're using no booster. And I updated the concentrations down here for some numbers from an RO reject water that we did test in our lab to see how foam fractionation would perform. So I'm going to start sounding like a broken record here, but if you don't use any booster, you may need a carbon polish to hit those 4 nanogram per liter discharge limits. But you can see even with that carbon polish, the SAFF line crosses at about 3 years. All the lines kind of meet at about 3 years, and then going forward, your foam fractionation costs are lower. So that's an advantage of using foam fractionation. Now, as we've discussed, the cationic booster is going to be your highest removal rate. So if we switch to the cationic booster, we see that SAFF curve flattens out. We've eliminated the need for the carbon polish, so our costs are lower over time. And now we're at about a 2-year payback period versus the GAC and ion exchange resins. But because you're using this for drinking water, maybe it's not a great candidate site for a cationic surfactant because a lot of times treated RO reject water needs to get blended back into the drinking water supply to add salts and things back in. So you're probably not going to be able to use the cationic surfactant. So if we look at the non-ionic surfactant, we see that line jumped up a little bit because we do need that carbon polish. We're not quite hitting 4 nanograms per liter. We're hitting 9 and 12, so we're pretty close, but not quite there. So we do need a carbon polish, but you still save a lot of media by adding the booster that you would versus just foam frac alone. So you see here on the breakdown with the SAFF polish, we're using about 15,000 pounds of carbon per year with the SAFF plus carbon versus 97,000 pounds of carbon for the carbon only system and about 60,000 pounds of resin. So your payback period with the non-ionic booster is just over 2 years for the SAFF capital costs versus those less expensive media-based systems. So this is the general overview of the calculator, how it works. Like I said, there's a lot of different things we can tweak and test. If you have your own site data, we're happy to walk through this, fill in your site data, your electricity costs, your labor rates, your carbon absorption rates, your price you pay for carbon, all these different factors. If you already know your capital cost for carbon, or if you've already installed the carbon and your capital costs are zero, we can put all those different factors in and figure out what's best for your site.
Yeah,
Now,
I think
with
maybe
that,
just maybe another comment that responds to a question is that you know there's assumptions in certain cases that are made with the PFAS concentrations, but if you have your own water analysis, if you have or if you don't and need assistance on that, and we have lab capabilities to do that. We also, you know, can, once we have that, we can update the tool. As Jason says, you know, just with more information, some of the assumptions go to, you know, to more factual based things, and the tool just becomes that much tighter. And that's really helpful to clients that we've worked with using this tool. You can change things, as you can see here, like the electricity rate in this case is 20 cents per kilowatt hour. But again, you'd be in a place maybe where that's different, so you're making adjustments here. But all of that will just refine things and make this a more accurate, up-to-date estimate. So there is another question that came in. Let's see. Does the booster impact the GAC polish performance? If so, does the calculator include additional GAC capacity to remove the SAFF booster?
So the short answer is no, it doesn't include that cost. And the reason for that is the booster should not affect anything downstream. So when you add a booster for foam fractionation, that the purpose of that booster is to enhance the foam. So the booster should be in the foam and in the concentrate that goes off for disposal. You should not have any residual foaming additive in your discharge water. If you do, you're adding too much. So it should not affect the carbon because it should be removed during the fractionation process and not discharged downstream to the carbon.
Okay. Jason, here's a good question that came in. Can scenarios of SAFF plus IX polish instead of the SAFF plus GAC, as the tool puts in, can that be analyzed?
In theory, yes. The way that it's set up right now, it's not set up to do it that way. You could tweak. You could do it in, you know, with some minor changes. You might have to do a couple iterations, but right now it's just set up to do a carbon polish. There's no reason you couldn't do SAFF plus IX polish. It's just not currently configured that way because that's not how we've done it. But if you just changed your capital cost to match what your ion exchange capital cost would be, and then changed this cost to be the same, the carbon versus the IX, it would functionally do what you're asking it to do.
Yeah. I would just say to the person that asked that question, if this is a scenario that you're interested in, if you're thinking about, you know, foam frac SAFF with and you're determining what the polish step would be, then reach out to us. I think, as Jason alluded to, we could make some assumptions and changes on the fly and give a look at what that would mean for you. So, yeah, awesome, Jason. Thank you for going through the tool with us. Yeah, I'm gonna hit on a few lessons learned here. This just kind of wraps together what we talked about. But you know, SAFF can be or can offer substantial cost savings over media-based sorptive solutions for a wide variety of media. So again, touched on, but wanted to emphasize, we talked a lot about the costs, typically lower and do not directly scale with PFAS concentration. So SAFF is highly effective and cost effective at giving more savings at those higher PFAS concentrations. And then you saw in a lot of cases the impact of that booster. It's a low cost add-on that can provide substantial savings through high PFAS removal. And the tool is able to say, hey, you use some booster and maybe you still need some polish, or depending on the booster that you choose, maybe you don't need it. But so the boosters can have a huge impact in effectiveness and overall cost. So, we've talked about this throughout the discussion today, but if you'd like a cost comparison for your site, we'd love for you to reach out. Whether this is your first time looking to improve your current system, or if you are looking at, starting from scratch. We've had clients that have systems that they've operated for a period of time. They've gone through substantial amounts of carbon and IX, or IX, and we're able to quickly say, hey, based on what your operating costs are, SAFF could help you in a big way and help quantify and monetize that for you. So in those instances, the data that you'll need would be your water type, required flow rate that you need, and your primary treatment goals. The tool can take over from there, but it's great to have discussions. I'll just say that we've had several really great discussions where, in talking with clients, things come out on just the benefits of this tool, and can be really eye-opening as it relates to cost savings for clients in the future. So the things here for a cost analysis setup, if you could, if you're able to, please reach out to us, and we're happy to go through the tool with you in detail. So Jason, thank you for taking the time to walk through this with myself and those on the call. So really, that concludes the time that we have today. Again, thanks to Jason. You're going to receive a follow-up email tomorrow with a link to the recording and any responses to questions that we couldn't cover today. A survey will also pop up on your screen. We'd love to hear your feedback. Take a minute to fill that out if you can. This is we've been doing these on average once a quarter. This is the first time we've showcased the calculator, but we really have taken feedback from these webinars and helped to kind of shape these discussions and scenarios moving forward. So we look forward to your feedback. But again, thank you. Have a great day. And again, we really appreciate you joining. Take care.